Hello, and welcome to the January webinar presentation by the Underground Construction Association Younger Members Group. My name is Colin Sessions, and I am one of the members of the UCA of SME Standing Committee for Younger Members. I am joined by Anthony Bauer, the Chair, Shannon Goff, the University Outreach Chair, Everett Litton, the Membership Chair, and Demetrio Kruscalo, the Media Chair. UCA of SME is a standing committee of younger members whose goal is to attract and develop engineers and construction professionals under the age of 35. Each month we put on a free webinar on various tunneling topics that are available to all interested parties. Before we begin this month's webinar, I have two quick announcements. Once again this year, the Younger Members Group will be offering a scholarship for students to attend the RETC conference in June. Information on the scholarship will be available next month on our website, so if you're a student, look out for it. If you know someone who might be interested, please let them know. For those of you who logged in early to the webinar, you saw a flyer for next month's webinar. Mike Miller from Citizens Energy Group will be presenting on the Indianapolis's Dig Indy program. That'll be the first Wednesday in March instead of the last Wednesday in February due to a scheduling conflict. There will be more information on this webinar as we reach closer to the date. Today we have Dr. Kapila Pathirage, and he will be discussing horizontal directional drilling. Dr. Pathirage is a principal geotechnical and tunnel engineer at CDM Smith. He has over 25 years of experience in the geotechnical and environmental construction consulting industry. His work includes a wide variety of geotechnical and environmental projects for public and private sector clients throughout the United States and globally. His experience includes projects involving tunneling, microtunneling, horizontal directional drilling, dams, deep shafts, deep and shallow foundations, excavation support systems, soil improvement, and 2 and 3D modeling. Dr. Pathirage, thank you for presenting for us today, and when you're ready, please share your screen.
Thanks, Colin. Good morning, everyone. Good afternoon, depending on where you are. Thank you all for taking the time to attend this. Can you see my screen now?
Yep, I can see it.
All right.
It looks good.
Thanks. Thank you all for taking the time to attend this webinar today. My name is Kapila Pathirage. I'm a professional engineer with over 25 years of experience in the geotechnical and in the tunneling field. The title of the webinar is Horizontal Directional Drilling, a Feasible Method for My Project. We have been asked various questions on this topic in the past. One of those common questions is, can the horizontal directional drilling or the HDD method be used for my project? The intent of this webinar is to provide you with information on HDD concept, so you get a basic understanding on the HDD method, design aspects, and construction aspects. This is the outline for the webinar today, Horizontal Directional Drilling Overview or HDD Overview. Here I'm going to talk about what the HDD method is and what is involved in the HDD process. The next topic is planning and design. I'm going to talk about what goes into planning for HDD project. Then I will discuss the HDD design components and what is involved in a HDD design. Construction documents and contract documents and construction. Once the HDD design is done, the next step is to prepare contract documents, select the contractor, and do the construction. I'm going to walk you through these components as we go along with this webinar. Schedule. I'm going to discuss what is involved in a typical HDD schedule. The next topic is CDM Smith HDD design and construction experience. I plan to discuss a couple of HDD projects that CDM Smith completed over the last few years, and also I plan to discuss an ongoing HDD project. Last, we'll have a Q&A session to answer the questions that you may have on the HDD method. Let's start with the horizontal directional drilling overview or HDD overview. What is horizontal directional drilling? Horizontal directional drilling is one of those trenchless methods. This method was developed in the 1960s by the oil and gas industry. HDD typical applications are installation of gas lines, cables, electrical conduits, water pipelines, and sewer force mains. What is the practical range for HDD? Pipe diameters ranging from 2 to 60 inches can be installed via HDD method. The crossing length can range from a couple of hundred feet to few thousand feet. Typically, it can go up to 10,000 feet. In terms of ground conditions, HDD operation is favorable in sandy, clay soils and in rock. However, subgrades that contain man-made obstructions or boulders or weathered rock are not recommended for HDD operations. But this does not mean that the HDD method cannot be used for your project. You may have to take additional steps or additional evaluations to ensure that the HDD method can be used under these conditions. First, let me introduce you to some of those HDD terminology. This is a typical HDD vertical alignment. This side is the pipe side where the pipe strings are assembled, and this is the pipe entry angle at which the pipe would enter the borehole. This is the start of curve right here and the end of curve, and this is radius of curvature. This is a predetermined bore path that the pipe would travel from one end of the alignment to the other end. This is the rig side where the rig is placed, and this is the pipe exit angle at which the pipe would exit the borehole. This horizontal segment is called pipe spring line elevation, or the deepest portion of the HDD vertical alignment. How HDD is done? HDD is performed by drilling equipment that is capable of being operated horizontally and vertically while drilling to direct the path of the crossing along a predetermined bore path. As you can see on this slide, HDD method has 3 steps: pilot hole drilling, hole enlarging or reaming, and the pipe pullback. This is the first step, pilot hole drilling. How we can do this? Place a rig on one end of the alignment and start the drilling the pilot hole. Pilot hole diameter varies. Typically it varies from 4 inches to 12 inches. The second step is hole enlarging or reaming. Reaming typically starts after the pilot hole is done. What is the purpose of reaming? The purpose of reaming is to enlarge the borehole to the required diameter to facilitate the installation of the product pipe. How do you estimate the required diameter? The rule of thumb is to enlarge the borehole diameter to 1.5 times the product diameter. This rule applies to pipe diameters up to 24 inches. What you would do if you have a pipe diameter greater than 24 inches? The simple rule is that add 12 inches to the pipe diameter to estimate the required borehole diameter. The third step is pipe pullback. Once the borehole is enlarged to the required diameter, the product pipe can be pulled through the borehole. This slide shows all 3 steps: pilot hole drilling, reaming, and the pipe pullback. The next topic is planning and design. Let's see what goes into planning for HDD job. In my view, the planning stage for HDD job is very critical to the success of the project. As you can see, there are many things on this list. Need to do a route evaluation and land use evaluation. Need to understand where the potential wetlands are. Need to obtain easements for the project. Need to obtain the required permits. There are a lot of permits usually for HDD job. Need to understand where existing utilities are. These are one of those concerns, prime concerns when we plan for HDD job. And also need to identify if there are any man-made obstructions such as foundations or bulkheads or along the proposed alignment. Usually these bulkheads, if you have to go across a river, probably you might have some piles or bulkheads. You want to make sure that you identify those locations. This is also very important. Need to conduct a desktop study. In addition, you should have a good handle on the project requirement. This means approximate length of the crossing, pipe type, internal pressure of the pipe, the pipe diameter. Speaking of a desktop study, what is the purpose of this study? The intent of a desktop study is to find the information on geology in the project area and the existing information near the project site. For example, you can check USGS maps. This would help you to get an idea about the subgrade along the proposed alignment. And you also can look for construction records near the project site to see if any geotechnical boring information is available. In addition, I would conduct a field reconnaissance. If making a site visit is difficult due to some reason, what you can do, you can take a virtual tour around the site using Google Earth. This would help you to identify the potential site constraints such as overhead lines, bulkheads, all foundation. Also, this would help you to identify potential work areas for the project, such as areas for placing the rig and for laying down the pipe. Typical pipe types for HDD use are fusible polyvinyl chloride or fusible PVC pipe, high-density polyethylene or HDP pipes, steel pipes, ductile iron pipes. But each pipe type has limitation based on their operating requirements. Pipe length, pipe diameter, internal pressure, corrosion requirement. So you need to look at those things when you're planning for a HDD job. The next topic is HDD design. Typically, HDD design starts upon finalizing the horizontal alignment for the project. This is a typical horizontal alignment. After a desktop study, you should have a good idea about the anticipated subgrade condition along the proposed alignment. So you'd be able to plan a subsurface investigation such that would supplement the existing information. Otherwise, you got to plan on drilling adequate number of borings to obtain the required information for the design. Typically, boring spacing can be ranged from 300 feet to 500 feet. The depth of boring varies. Typically, it goes between 3 to 50 feet deep. However, sometimes it can go as deep as 150 to 200 feet from the ground surface. One important note, no boring should be taken right on the HDD horizontal alignment. The reason is that we want to avoid any potential frac out conditions during the HDD construction. Let me briefly discuss what is frac out. Frac out is an inadvertent return of drilling fluid to the ground surface or to a water body. Typically, a frac out is not allowed by environmental regulation that are enforced by most of the states. So we must take necessary steps during the design to avoid such from happening during the construction. Let me get back to our discussion on the subsurface investigation. Once the subsurface investigation is done, the next step is to select samples for lab testing. Typical soil testing would include grain size analysis, Atterberg limits, organic contents. If cohesive soils are encountered, you may want to do triaxial test. In the event your HDD alignment is supposed to go through rock, you should plan on doing some rock testing such as unconfined compressive strength of rock, Searcher abrasivity index test, splitting tensile stress, point load test. If possible, plan on conducting petrographic analysis, because this is a very useful test because it takes time to do. At least it takes about 3 weeks to do, and a little bit expensive, about $275 per test, but it gives you a good understanding about rock minerals. You can get a good idea what kind of contractor actually can get a good idea on what kind of tools he can use for drilling through the rock. Okay, let's discuss HDD design components and what is involved in a HDD design. HDD design would include developing a subsurface profile, preparing a geotechnical data report, conducting frac out analysis, establishing the HDD vertical alignment, estimating pullback forces, and also conducting pipe stress evaluation. Typically, pipe stress evaluation includes 2 types of analysis. These are applicable for plastic pipes, fusible PVC or HDP pipes, estimating axial tensile stresses and estimating wind deflection, both short-term and long-term. This slide shows an illustration of a subsurface profile. Once the geotechnical data are available, both field data and the lab data, we would develop a subsurface profile along the proposed alignment. like this one shown on this slide. We typically develop this profile on one-to-one scale because it helps us to understand the subgrade, especially to understand the areas that might give us potential troubles during the construction. What do I mean by understanding the areas with potential troubles? When we evaluate the subgrade, we would like to identify if there are any areas that may contain loose soils, gravel zones, cobble zones, boulder zones, or potential voids along the proposed alignment, because those conditions may not be favorable for HDD drilling. So we want to identify the solutions during the design, so those solutions can be incorporated into the design in such way that would mitigate potential construction difficulties down the road. Let's discuss Geotechnical Data Report, or GDR. Typical GDR for a HDD project includes few sections: table of content, background, project datum, description of soil classification system, or if you have rock, you need to talk about rock classification system, and also you need to talk about description of drilling and sampling procedures and lab testing procedures. Also need to provide boring logs. Usually we develop these boring logs on Gantt software, and also you need to include the data from lab testing as appendices. Once the GDR and the subsurface profile are complete, the next step is to conduct frac-out analysis. To conduct frac-out analysis, we select critical sections along the HDD alignment, and also we select an initial depth for the pipe spring line. We used a computer software 2D finite element program to conduct this frac-out analysis, but you can do hand calculation. There are methods to do that. And if you have a 2D software like GeoSlope or GeoSlope Suite or something, you can use that. Once the model is developed, soil parameters, running this model may give you an output like this one shown on this slide. This is an example of a frac-out condition. That means drilling fluid would escape to the ground surface. If you are going under a river, might escape to the water body. So what you do if you get a frac-out condition like this one during the design stage? The short answer is you can lower the pipe spring line. You can lower the pipe spring line, or in other words, increase the soil overburden thickness over the pipe. Then rerun the model until no frac-out condition is observed. This analysis is kind of an iterative process because we got to find the optimum elevation for the pipe spring line, as the project cost can go up with the increase of the soil overburden thickness over the pipe. Let's see what is involved in developing the HDD vertical alignment. After the subsurface profile evaluation, we have an idea about the subgrade zone that is favorable for HDD drilling. After the frac-out analysis, we have an idea about the subgrade zone that is free of potential frac-outs. So we use this information to identify the preferable vertical window for placing the pipe spring line. Then we select entry angle, exit angle, radius of curvature to develop the HDD vertical for conducting the remaining parts of the HDD design. What are those remaining parts? Estimating pullback forces and conducting the pipe stress evaluation, such as axial tensile stresses and ring deflection. The pullback force evaluation and the pipe stress evaluation are involved in a complex calculations because they require not only the understanding of the soil or rock behavior, but also the understanding of the pipe material behavior and the soil-pipe interaction behavior. Several design guidelines are available for estimating pullback forces and conducting pipe stress evaluation. As shown on this slide, there are guidelines such as ASTM guidelines, PPI guidelines, Plastic Pipe Institute, and ASCE guidelines. Also, North American Society for Trenchless Technology, they have published guidelines such as HDD Good Practice Guidelines. The next topic is contract documents and construction. Contract documents includes drawings, specification, and the geotechnical data report. Typically, drawings would include a plan view that shows the HDD horizontal alignment and a profile view that shows the HDD vertical alignment. HDD vertical alignment should show station at start, station at end, entry angle, and exit angle, radius of curvature, pipe springline elevation, pipe diameter, and the pipe type. Regarding specifications, HDD portion of the project would include HDD specification and the pipe specification. So also you have to have a front end. You can talk with your PM what front end document should be included for the project. The next topic is HDD construction. HDD projects can be design bid build or design build. Design bid build scenario would include the client, the engineer, and the general contractor or the HDD specialty contractor and the pipe supplier. In my view, HDD specialty contractor's experience would play a big role in the success of the job, but the trick is to find an experienced HDD contractor who is familiar with the geologic condition of the area where the project is in, and also who has a good track record in the HDD construction. Let's discuss some of those recommended activities that we would do prior to the construction. In my view, having a pre-construction meeting with the contractor is useful because this could discuss safety, potential risk, any modifications to the design, coordination matters, who is talking to who, and the submittal review process. Also, this is an opportunity for you to ask questions prior to the start of the construction and try to get answers from the contractor. The other activity we would recommend is to conduct risk mitigation meetings. These meetings are typically conducted after the contractor mobilized to the site. As you can see, there are few such meetings prior to pilot hole drilling. So you could discuss all this risk during the pilot hole drilling and talk to the contractor. And prior to reaming, we would like to have another meeting prior to reaming, also prior to pullback. And once the pullback is done, you can have another meeting prior to testing. This is one of those requirements that one should include in the HDD specifications. You have to have this requirement in the specification because otherwise contractor won't listen to you even if you want to conduct these meetings. If the project is a complex one, I would recommend you having these meetings in the field trailer face-to-face with the contractor. If it is a less complicated job, you can do this via teleconferencing. Also, there are typical activities during HDD construction. So activities like pipe layout, pipe fusing, and pipe staging, equipment layout, surveying equipment and procedures, pilot hole drilling, reaming, there's a big list here, drilling fluid and contact grouting, soil separation plant, disposal of soils and drilling fluid, pipe pullback, ballasting the pipe, and pipeline cleaning and testing. This slide shows a typical equipment layout for HDD job. This is the pipe storage, this is a control cabin, this is the drill rig, this is a soil separation plant, these are frac tanks, and this is the mud pump, and this is loss circulation material. It's a kind of a storage here. This slide shows surveying equipment for tracking the drill head. The drill head would have to be tracked in order to be on the predetermined bore path. This can be done using a walkover system or a paratrack system, this is a commercial name, and also a gyro system. This is an illustration of a pilot hole drilling. I would recommend including the language in this spec that the contractor would provide you daily logs and records like this one at the end of each workday. Also, you want to make sure that you get them reviewed by the design team timely manner to see if there are any red flags. This slide shows reaming. Reaming can be done using a single pass or using reamers in tandem. These are some pictures of those reamers. This is a single pass reamer. This reamer, these are reamers in tandem. This is an illustration of a pullback, pipe pullback, and this picture shows pipe pull head, and this picture shows pipe staging, and this is a pipe fusion machine, and where you can assemble pipe strings. This slide shows a summary of construction activities. As I mentioned earlier, this is the pipe side and this is the rig side. These activities are typically conducted on the pipe side. These activities are typically conducted on the rig side. One important note to remember, the contractor should carry out both of these activities at the same time so the project can stay on the schedule. This means place the rig on the rig side, drill the pilot hole and ream the borehole to the required diameter, and at the same time contractor should start fusing the pipe in order to make the pipe strings, and the strings are complete. He has to do a low air pressure testing. Once the testing is done, these pipe strings should be staged for the pullback. This picture shows a typical pullback operation. Typically, pullback is a continuous operation if the project includes only one pipe strings. But sometimes you would need to assemble few pipe strings due to an insufficient staging area. In such case, pullback would have to be stopped to attach those pipe strings together. The next topic is construction schedule. Let's see what is included in a typical HDD schedule. You would need to obtain permits for the construction. This permit process may take up to 6 months depending on the location of the project. And preparation of contract documents may take up to 3 months. This would include planning and executing a subsurface investigation, preparation of geotechnical data report, conducting the HDD design, and the preparation of the contract documents. This slide shows a typical HDD construction breakdown. Typical mob takes about 5 to 8 days depending on the size of the job. Pilot hole drilling production rate varies between 100 to 200 feet a day, and I'm talking about this pilot hole production rate in soils. It's depending on the type of the soil. It may go between 100 to 200 feet a day. We usually assume the same production rate for reaming. If you have to make a schedule, I would assume the same rate for reaming. Pipe assembling may go between 100 feet to 300 feet a day, and pipe fusion can take about 1 to 3 hours per joint depending on the pipe diameter. Pipe pullback takes about 1 to 2 days. Also, pipe testing takes about 1 to 2 days, and demob takes about 3 to 5 days. The next topic is CDM Smith HDD design and construction experience. We, CDM Smith, have involved in designing many HDD projects throughout the country. I have selected few projects for this webinar to show you the HDD design and construction aspects. The first project that I am going to discuss was completed in New Jersey. Crossing length was about 5,360 feet. Pipe type was about fusible. Pipe type was fusible PVC, DR18, 24 inches in diameter. The total construction cost was about 4.7 million. This slide shows the HDD horizontal alignment. This is a blue line. As you can see, we took 11 borings. 3 borings were on land and 8 borings were over water. After completion of the geotechnical investigation program, we develop a subsurface profile along the proposed alignment. We ran frackout analysis to understand the preferable vertical window for placing the pipe spring line. Finally, we decided to place the pipe spring line at elevation -60. We designed the HDD vertical alignment using entry and exit angle of 8 degrees. After that, we ran the pullback calculation to estimate the pullback forces. For the calculation, we initially assumed that the pipe was empty during the pullback. The results indicated that the estimated pullback forces would exceed the manufacturer's recommended pullback forces for the respective pipe type. Typically, plastic pipes, when they are empty during the pullback, would contact the borehole walls due to the buoyancy. So this would increase the friction acting on the pipe As a result, pullback forces will go up. So what are the choices that you have during the design to address this issue? The choices are: use a stronger pipe or ballast the pipe. Let me explain what these are. A stronger pipe means a pipe with a thicker wall. A thicker wall means higher recommended pullback forces by the manufacturer. Ballast means fill the pipe with water during the pullback. This is a method to keep the pipe centered in the borehole so the pipe would not come in contact with the borehole walls, which would result in reduction of the pullback forces due to the less friction acting on the pipe. So finally we decided to go with ballasting the pipe because that was cheap and ran the calculation. Finally we selected DR18 fusible PVC pipe for the project. This picture, the left one, shows the rig side. This is the 130,000 pound rig that we used to drill the pilot hole. This is the control cabin. These are drill pipes. This is the soil separation plant. We used 2 rigs for this project. This picture shows the other rig. This is the 880,000 pound rig that we used to ream the hole and pull the pipe back. This is the pipe fusion machine that we used to assemble the pipe strings. This picture shows that the pipe strings are staged for the pullback. We had to prepare 4 pipe strings as the available pipe laydown area was not large enough to accommodate the full length of a single pipe strings. This means we had to stop the pullback operation 3 times to attach those 4 pipe strings together. Each stop took about 2.5 to 3 hours. This picture shows the carrier pipe is ready for the pullback. Portion of the pipe is typically put on rollers. As you can see, rollers were suspended from excavated and mobile cranes because the ground was hilly and uneven. The pullback operation took about 23 hours. This picture shows the end of the pullback as the pipe exceeded the borehole on the rig side. The second project that I am going to discuss was completed in New York. The crossing length was about 2,276 feet. The project required installing the carrier pipe in a casing pipe. First we installed the casing pipe. The casing pipe was steel, 24 inches in diameter. Then we installed the carrier pipe. The carrier pipe was ductile iron, 12 inches in diameter. The total construction cost was about 6.5 million. This is the horizontal alignment. As you can see, we took 6 borings. 2 borings were on land and 4 borings over water. As I indicated earlier, no borings were taken right on the HDD alignment due to the concern for a potential frac out. After completion of geotechnical investigation program, we developed a subsurface profile along the proposed alignment. We ran frac out analysis in order to understand the preferable vertical window for placing the pipe spring line. Finally, we decided to place the pipe spring line at around elevation minus 120, which was in rock. This rock was Manhattan schist. We designed the HDD vertical alignment using an entry angle of 18 degrees and an exit angle of 14 degrees. The radius of curvature was 2,400 feet. Typically, the radius of curvature is a function of the drill pipe diameter, but in some cases, the radius of curvature is a function of the pipe material. This is one of those some cases that the pipe material governs the radius of curvature design. The casing material was steel and the pipe diameter was 24 inches. For steel pipes, the rule of thumb is to use 100 times the pipe diameter to estimate the radius of curvature. So we established the HDD vertical alignment using the radius of curvature of 2,400 feet. Using this HDD vertical alignment, we ran the pullback calculation. The results indicated that the estimated pullback forces would exceed the manufacturer's recommended pullback forces. So we decided to ballast the pipe. Since the steel pipes are heavier than the plastic pipes, we kind of knew that we do not have to ballast the pipe 100% of its volume. So we ran the pullback calculations assuming 25% of ballast, 50% of ballast, and 75% of ballast in order to find the optimum case for ballast in the pipe. Finally, we decided to go with 50% of ballast for the pipe pullback. After running the pullback calculation, pipe stress evaluation, we selected a steel pipe with wall thickness of 0.375 inches for the casing pipe. This is the rig site. We used 1 million pound rig to drill the pilot hole, ream the hole, and pull the pipe back. These two pictures show the pipe side where the pipe strings are assembled. These are steel casing pipe, 24 inches in diameter. The third project that I am going to discuss is an ongoing HDD project. This project is in New Jersey. This is a design build project that we have teamed up with a HDD contractor. This project includes installing a new gas main via HDD. The pipe diameter is 12 inches. The crossing length is about 14,400 feet long. The total design and construction cost is about 12.2 million. This slide shows the HDD horizontal alignment. Through a desktop study, we could find existing boring information from a nearby bridge construction. Based on that information, we developed this subsurface profile, so we kind of knew what to anticipate along the proposed alignment. We decided to take 5 borings to supplement the existing geotechnical information that we have in our hand. 3 borings were over water and 2 borings were drilled on land. Land borings were drilled to about 62 feet below ground surface, and marine borings were drilled to about 152 feet below the mudline. As you can see, all these borings were placed away from the proposed HDD alignment. In some cases, we went north 700 feet to north and 750 feet to north, and this one was placed for approximately 400 feet to the south. This slide shows some of those HDD drilling concepts that we would consider for this project, since the crossing of this job is about 14,400 feet long. As you can see, there are 2 HDD segments, segment 1 and segment 2. Length of each segment is about 7,200 feet long. The plan is to construct the first HDD segment, then move on to the second HDD segment. Once these 2 segments are done, the plan is to connect them together in the middle of the bay using a steel cofferdam. To do the construction for the first HDD segment, we also plan to place a rig on one end of the alignment and another rig in the middle of the bay right in here. Then we plan to do an intersect drilling. Let me explain what the intersect drilling is. This means the pilot hole drilling would start from both ends of the HDD segment. So one hole is going this way, other hole is going in the opposite direction. So the idea is to meet these 2 drill heads somewhere in the middle of the alignment and make one long drill string. Once the pilot hole is done, we can start reaming. Once the reaming is done, we are going to pull the pipe back. The pipe will be pulled from the barge. Barge will be located right in the middle of the bay. The pipe will be string out on land, then it will enter the borehole right in here, so you can pull the pipe from the barge. So we would take the same approach to do the second HDD segment as well. We ran a fracked out evaluation and decided to place the pipe spring line at around 60 feet below the mud line. We used 14 degrees for entry and exit angle. 12,000 feet for the radius of curvature to design the HDD vertical alignment. This slide shows the respective HDD vertical alignments. We have two segments. This is the segment 1 and this is the segment 2. This slide shows a plan view and a cross-sectional view of the proposed steel coffer dam. Water is shallow in this area. Water depth is about 5 feet. We plan to excavate down to about 6 feet below the mud line to connect the two pipes segments together. Then we plan to we plan to place a backfill over the pipe so the soil cover on the top of the pipe can be minimum of 4 feet in thickness. This slide shows the anticipated construction steps for the pipeline connection. The first one, this one, shows the construction of the pipe segment is complete and the temporary coffer dam is in place. The second sketch, this one shows the system is ready for the excavation, and the third sketch shows the excavation is complete, and this is the fourth sketch. This one shows the pipe, those two pipes are connected and the backfill over the pipe is complete. The last sketch shows the steel sheathing is removed and the pipe is restored to the original condition. This concludes the webinar on HDD. I hope that you enjoy the webinar. Hopefully this would be useful for you to plan your next HDD project. If you have any questions, please feel free to ask.
Thank you so much for that wonderful presentation. We would like to ask all of our attendees right now to go ahead and use the chat panel to submit any questions you have for our speaker, and we'll read them off to capture those in our recording. As we are recording today's session, we will email everybody who's attended today when the recording is available on the UCA Young Members website. I had a question entered earlier. I'm hoping that Gabrielle will resend her question to me. She had a question about radii, but I can't remember which slide it was on. So Gabrielle, if you're still with us, if you could submit your question again, we'd be happy to get our speaker to go ahead and help answer that question. Okay, well right now it looks like we don't have any questions coming in. Gabrielle, would you like to make any, oh wait, here comes the question. Oh, here we are. What typical, okay, so the question is, what typical curvature radii are?
Typically, when you look at the radii of curvature for the exit and entry and exit angle, first thing you need to look at what is the pipe type. If you use plastic pipes, you can use for HDP pipes, that's a 40 times outside diameter. For fusible PVC, it's a 25 times outside diameter. But you have to understand what kind of drill pipes you are going to use for your project. Let's say, for example, right, you are going to install fusible PVC pipe, 20-inch fusible PVC pipe, and that radius can be around 600 to 800, above 600. But you need to think about what kind of pilot hole diameter you are going to use. It depends on, basically it depends on the type of pilot hole diameter that you are going to use for your job. Especially when you use steel, the rule of thumb is to use 100 times the 100 times the steel rod diameter. If you use pilot hole diameter, if you use 4-inch diameter rods, you can use minimum you have to use 400 feet of radius. There are some cases you have to use 8 inches in diameter for steel rods. Then you have to make sure that your radius is 800, minimum of 800, even though you can go below that if you are going to use HDP pipe. That is the that is the point you need to understand when you are designing HDD curve, HDD vertical alignment for your job.
Wonderful. Thank you so much. The next question regards the last project example. Why not use microtunneling or other longer range methods to avoid the need for connecting two drives?
We are talking about 14,400 feet long crossing. Yes, you can use microtunneling. If you use microtunneling, you have to have intermediate shaft probably every 2,000 feet, 2,500 feet. That means a lot of shaft you have to construct, that the project cost is going to go up. So when you are planning for a job, other option is to do a tunnel. And this is a gas main only 12 inches in diameter. If you have to do a tunnel for this kind of length, you may have to use a TBM. So TBM, what's the minimum diameter TBM? Probably at least you should have about 9 to 10 feet diameter TBM. Again, TBM is going to cost a lot, and also for a 12-inch diameter pipe, doing a tunnel probably not cost effective. When you're planning a project like this, always we look at all these options. At the end of the day, we take the cost-effective method.
Thank you. The next question reads, can this process be modified for gravity sewer applications? Microtunneling?
Typically, HDD cannot. I would not recommend using for gravity pipelines if you are going to use HDD method. If you are using microtunneling, yes, you can design gravity pipes via microtunneling.
Wonderful. Thank you so much for that. That seems to be all of our questions at this moment, but we'd like to invite the attendees to use the email addresses to reach out to other experts if you have any other questions on this subject. And it looks like we have a few people that are saying thank you. They really appreciate your presentation. Capulet, would you like to make any closing statements?
Yeah, I'm really glad that I got this opportunity to present this webinar. I hope you enjoy the webinar. Hopefully content is useful for you to get some information out of this webinar. If you have any questions, please feel free to contact me anytime. You can call me or you can email me, and I'll try to help as much as I can. And thank you all for taking the time to attend this webinar.
That's wonderful. Thank you so much. This was a very informative presentation. And again, we were recording today's session, so we'll be sure to email everybody when it's available on the UCA Young Members website. Let me go ahead and take that presentation role back now, and I'll just go ahead and share the application really quick just to let everybody see the homepage of the UCA Young Members website. All of their events are recorded and available here under the past webinars page. So you can check out these videos at your convenience. And please reach out to our speaker. He's got wonderful amounts of information on this subject. And thank you again, everybody, for joining us today.
Thank you very much, Heather. Thank you very much, Colin.